Professor, is there going to be a quiz over the weekend?
No.
Okay, thank you. That's how I like it. Oh, man, you make fun of me then? Oh.
Next semester. I like my professor. He's really good. I need to start taking my prereqs. Yeah, I'm gonna
go, Sarah? What is this? Oh, is that after this? I guess. I know. It's either that or... Okay, I guess I'll do it.
Okay, good morning everyone. Good morning. Thank you for coming. Your exam is open, okay, on carbon. So if you go on carbon quizzes, you'll see your exam. I will not talk much about it today, but we can talk about it on Wednesday. Okay, once I see how your performance is and so on. But in my opinion, I just want to say it out here that it's relatively straightforward. Okay? Good luck. Alright, so I'm going to continue talking about these bending stresses and transverse shear stress. We are still getting used to some of these equations. So today's problem is going to be once again on how to use those equations to come up with the state of stress at certain points on a volume, on a cross section. Okay? Starting from Wednesday, we will look at problems where I have a lot of loads acting with numbers on it. And then I will start drawing the shear force bending moment diagrams and go through similar types of motions. Next week, I'm going to do three-dimensional combined loading problems, where you take a section of a pipe, apply all these loads, and see how the stresses change. Okay, so those will be a little more hairy, in my opinion. And then we're slowly getting to the end of the semester. Some of us can't wait for it. Okay, completely understandable. Time flies, yeah, time flies. I mean, it's like we just met last class, yeah. All right. So as we go to the end of the semester, there are two topics of critical importance, something that you will use in your future courses, okay, which is called principal stresses, which tells us, okay, what are the largest stresses that act on a body, and how does this inform the failure of the body. Okay? So I want to get to that particular topic, come rain or snow, hopefully not snow. And then at the end of the semester, if we have some time, maybe a couple of lectures, I will talk about bending of beams. The bending of beams is actually my specialty, but I fear that we may not have enough lectures to go deep into it, so we will have to make do with whatever is necessary to get us through. Okay? Alright, so here is another problem similar to from last time. Last time we looked at a rectangular cross section. This time I'm going to look at a circular cross section. So the next easier of the cross sections. The easiest is the rectangle. Next is a circle. Then we will start looking at some odd shapes. Okay, T sections and L sections and so on. So problem. This is once again on combined loading. In this problem I have a shaft, okay, with a circular cross section. Rather than making us draw the shear force and bending moment diagrams and figuring out, okay, where are the maximum moments and shear forces acting, they are already telling you, here is the cross section, these are all the forces acting. Okay, so I'm going to draw the cross section. Okay, so this is a cross section of a shaft, circular cross section. Let's say the radius is r. I'm going to draw the axis system. Okay, so here are the axes. I'm going to label them as y and z. And then the x-axis, according to the right hand rule, if I take the fingers of my right hand, slide from y to z, it's pointing into the page. Okay? So this is the x-axis. The following are the forces and moments that are acting on this cross section. So watch this. Firstly, I have a torque acting on the cross section. Okay? So drawing the torque. There is a torque T. Then I'm going to have two shear forces, one in the y direction, the other in the z direction, acting on the cross section. So look at this. So one this way. Let me call it as V1. Okay. And then I'm going to have another one which is coming along the negative z axis. So V2. Okay, people in the back, can you see my writing? Okay. So V2. Then I'm going to have two bending moments. One about the z direction. What does this signify? It signifies that this moment is acting, I'm going to call that moment as M1. Okay? This moment is acting in such a way that if I use the fingers of my right hand and I clutch the z-axis, my thumb is pointed along the positive z direction. Okay? So that's one bending moment. I'm going to have one more about the y-axis. Okay? This is bending moment M2. These are all the loads that are acting on this cross section, as you can see. And I have some points of interest on this cross section. So centroid C. Then let's say this is point A. Okay, let's call this as point B. Then point C is the centroid, so let's say this is D. And then I have point E on the other side. 9 o'clock position, so this is point E. The radius of the shaft is R. Little r, okay, is the radius of the shaft. I need to find the stresses at all of these points due to all these loads acting. Okay, so obtain. So obtain the stresses at A, B, C, D, and E. Okay, all of these points. Due to all these loads that are acting on the bottom. T is the torque. M1 and M2 are bending moments. V1 and V2 are shear forces. If you want to make this a little more dicey, I can add a normal force that is coming out of the page, but we already handled that in the last class. Okay, so it's not going to make a huge difference to your life. All right. So some geometric properties that we need to be aware of for a circular cross section. These I am not going to prove. They are fairly straightforward. If you look up any statics textbook, these will have been proved. Okay. So for a circular cross section, the moment of inertia, area moment of inertia about its axis of symmetry. Okay, so here is a circle. Let's say the radius is r, and then I have two axes of symmetry here. Z and y. The moment of inertia about the z-axis is going to be the same as that about the y-axis because it is a symmetric cross-section. and they're both equal to the following value. So I Z, usually people prefer to write it as a double subscript IZZ, so that's what you have seen in maybe statics, I'm not sure. I prefer the single subscript, but I'm just going to stick with what your book does. This is pi by 4 r to the power 4. And what will you notice here is that if I take this guy, and if I take that guy and add it up, what do I get? I get the polar moment of inertia, which is pi by 2 r to the power 4. Okay, so that's how typically these values are obtained, by saying that, okay, the polar moment of inertia is the sum of these two. It's a symmetric cross section. So if I know the polar moment of inertia, then I know the moment of inertia about the rest of the axis. The polar moment of inertia is about the x-axis. So if this is the x-axis, then we call it as J, right? So this is J is r by 2 r to the power 4. We did this derivation when I taught torsion some time back, so please do take a look at it if you'd like. And then you see that J xx iy plus izz. Okay. So this is the first geometric property that I want to talk about. So these are all area moments of inertia. The second one is the location of the centroid of a semicircle. Okay, so once again I have a circular cross section, radius is r. If I look at a semicircle, its centroid with respect to the axis of symmetry is given by the following expression. Once again, no proof. Okay, this is, we can prove it, but it's not worth our time right now. C is the centroid of the entire cross section. I'll call this a C semicircle or C prime. Okay, so C prime is the centroid of the semicircular portion. Centroid location of the semicircular portion. Assuming a solid cross section. And of course, we'll see what will it be for a hollow cross section as well, a hollow tube. We will be looking at problems of those sort too, but when we reach there, we will look at that. So right now, if the radius is r, the distance of C prime to C is 4r by 3 pi. This distance is 4r by 3 pi. Okay, where r is the radius of the circle. I was told that the boards have been repaired. I am a little afraid though of pulling them, but we'll see. If they are repaired, then I'll maybe slide this up and see. Okay. So these are the things that we need, geometric properties of circular cross sections. And now let's get on our journey of solving this problem. Okay. So first things first. We had a couple of formulae that we had written down. Just as a refresher, I want to see if I can sneak it in somewhere. Here, sigma is minus my by I about the neutral axis, that's one. Then tau transverse VQ by I neutral axis multiplied by T times tau. Okay, so that's one. Then you have your regular torsion formula, which you're going to be exercising in your exam anyways. So let's see. So tau torsion is Tc by J. Okay, can everybody see my writing in the bottom as well? It's a familiar formula, so I'm assuming I don't need to rehash it too much. Okay. So these are the things that we have, and then normal force. If you have a normal force, then sigma average is N by A. Alright, so these are the four formulas that we typically use. We also had looked at the average shear stress a long time back when we started the ME 2020 class, right? Which is tau average is V divided by A, the shear force by the area of cross section. It is typically not used. Then the obvious question is, why did we teach this? It is the most simplest formula to estimate shear stress as an average. But the more correct way of calculating transverse shear stress is using this formula. Alright. So in this problem you have to be very methodical. Okay, this is the only saving grace in all these problems. You'll have to start looking at the effect of each and every one of them and then figure out, okay, what are the stresses due to these things. Okay, so let me start looking at the effect of the torque first. It's the easiest of the lot because we know the direction of the shear stress due to the torque applied at each and every point. Okay, so if I draw it out, I have my 4 or 5 points of interest, A, B, C, D and E. Okay, these are my points of interest. I draw the direction of the torque as well, clockwise, given to me. If this is the direction of the torque, then what is the direction of the shear stress at each and every one of these points? It is going to be tracking the direction of the torque that is applied. Okay, so at each and every point, I will be drawing a tangent to those points. Right here, this is going to be the direction of the shear stress, so tau B, and look at my subscript. I'm going to call it as tau B suffix T for the time being. The T representing the fact that this is shear stress caused due to the torque. Okay, then likewise I'm going to do the same thing for each of these points. Tau D at T, then tau E and tau A. What's the shear stress at point C due to the torque applied? Has to be 0, right? It starts from 0 and increases linearly as I go towards the outermost circumference of the cross section. Okay? Yes. No, that is the centroid. So centroid is the center of the cross section. The neutral axis will pass through the centroid. Okay? So in this problem, I can have either this axis as the neutral axis, or I can have that, and I'm going to talk about that. I can have either one of them as a neutral axis depending on which loading situation I'm looking at. Okay? Alright, these shear stresses are all the same value, so I will not belabor that point. They are all equal to the following. Radius is R. So tau the magnitudes are the same, and I do the calculations. These are all due to the torque applied. These are equal to T times or by J, it's a solid cross section, so pi by 2 or to the power 4. And I can do a little bit of simplification. I don't have numbers, but please bear with me. We want to get through some of these generic problems before we start looking at numbers. Numbers kind of obfuscate things. The tongue twister. Confuse things. Simpler way. Okay. Alright, so I can do the simplification. So first things first, I want to write the directionality at each and every point. Okay, so this is where we need to be a little careful. So let me start with the point A, and I have my axis system, Y, Z, x-axis pointing into the board. So these are all the magnitudes. Yes, if you want, you can just call them as magnitude. Obviously, the directions are not the same, right? Because you can see that they're all in different directions. So let's start off with A. Now, A, due to the torque applied, is going to be in which direction? It is going to be pointing along the Z direction, because the arrow is pointing along the Z. The area normal is going to be in the direction of the x-axis, because that's the axis coming out of the cross section. So this is going to be tau Zx, which is going to be simplified as 2t by r cube. Then I do the same thing at B. B, due to the torque applied, what is the directionality for that? We don't associate a positive or a negative sign with shear stress. The arrow is a really important thing that distinguishes whether the stress is pointing up or down. The subscripts don't necessarily tell you that. Okay, as you can see. So for B suffix t, the shear stress is pointing in the y direction, negative y really, but y direction. Area normal is still x, so this is yx. Two t by pi r cube, same thing as before. Then I have two more left. So tau at D. This is going to be in the same sense as the shear stress at A, but the directionality, you have to watch out for it from the figure. Okay? So this is still going to be Zx. 2t by pi r cube, and then the last one, tau at E. This is going to be the yx. And tau C is 0. Okay, so these are all the shear stresses. Are there any questions on these subscripts here? The second subscript is always the direction of the area normal. Okay, either into or out of the page. The first subscript is the direction of the shear stress itself. Be wary of the fact that just saying tau Zx doesn't necessarily tell me whether the stress is pointing in the positive Z or the negative Z. Okay? For that I have to refer back to this figure. So this figure is really important to draw first. Alright, I'm going to do something that might be dangerous. Let me try though. I'm still around here. Yes, sir?
That's my question. Why is it, so what's the reason behind pi r cos 3?
For finding which one?
Pi r cos 3 in the denominator of that.
I'm just writing as much of a simplification as I can make.
Oh no, I mean like why is it r to the third?
Oh, because I had an r in the top, right?
Oh.
A numerator, right? So I'll keep this down a little bit, maybe I'll do one thing. It does seem a little scary from here. But can everybody see the board there on the top? Everything that is legible? A little bit lower?
Yeah, a little bit lower.
I see. If I make it any lower, then you're going to not be able to see much of this portion here. You can?
We can see it.
Okay, okay. So you want this to be lower or you want that to be higher?
Either.
Either. All right. Any better?
Yep. That's good.
There we go. All right. Okay. You're a tough crowd. All right. Okay. All right. So let's get cracking on the other ones. Okay. So now I'm going to look at the effect of the first shear force V1. Okay. So B. Now, in all these problems, when we did the rectangular cross section, we were like calculating the shear stress using the generic formula and then reducing it to the points of interest, right? So I'm not going to be doing that, okay? So here's my figure. Points of interest, so C, A, B, E and D. My question to all of you, we decided something last time. My question to all of you is this. First of all, if the shear force is V1, what is the direction of the neutral axis for the shear force? It will be perpendicular, fantastic. It will be perpendicular to the shear force. So something to keep in mind, if I have a shear force, the axis that is the neutral axis for this shear force is the z-axis, which means if I'm looking at that other shear force V2, the y-axis is actually the neutral axis. For this cross section, it makes not much of a difference because the values will end up being the same in some sense. But if I have an odd-shaped body, which we are going to look at, like a T cross section or an L section or a C section, makes a hell of a difference as to what is my neutral axis. Okay? All right. Yes?
You're just having a slight point of confusion. You just mentioned that the y-axis is going to be the neutral axis.
Not for this one.
That's for the one above.
For the one above. Right. So, for this one, so maybe let me write down that statement. So, if I look at bending stresses, the axis of the bending moment is the neutral axis for that particular bending moment, bending stress calculation. Okay? If I look at shear stresses, the direction of the shear force perpendicular, this is my symbol for perpendicular, okay, to the neutral axis. So in my case here, for this particular problem, this is the neutral axis. My first question to all of you, after this information has been written down. At the end of class last time, on Friday, we said something about a rectangular cross section, right? If I take any point on the outer edge of the rectangular cross section, what is the shear stress due to the transverse shear force? Or what do you remember of a rectangular cross section shear stress distribution? What do you remember of that from last time? Yes?
Doesn't it decrease as it goes up?
Decreases as it goes up or goes down from the axis of symmetry, fantastic. So the shear stress distribution, we showed it for a rectangular cross section, and that's the holy grail of all cross sections. It will be the same behavior for any cross section. It will be the largest at the neutral axis for that particular shear force. And as I go to the outermost edges, the shear stress is going to become 0. So which means that this fellow is not going to have any influence on the point A or the point B. But it will have an influence on the point B and the point E, because they are points on the neutral axis. Okay, and if you want, you can think of it this way. Okay, so let's do a very quick calculation. So because I see that maybe I'm not playing my point properly here. So let's say that I calculate tau A. PQ by I, neutral axis times T, tau. If I think of the point A, first of all, if I want to calculate Q, Q is defined as A prime times Y bar prime, the first moment of the area. A prime times Y bar prime, where A prime is all the area either above or below the point of interest. Do you have any area above the point A? automatically this is gone. This is history. Okay, so Q is A prime y bar prime, so this is all the area above or below point A for our situation here. And so this is essentially going to be 0 because there is no area above. If I had chosen it below and if I did the calculations, it will end up being 0. There is no need for us to rehash that idea. So this is 0. Does this make sense to you? And the same is true for a rectangle as well. If you look at the top or the bottom of the rectangle, what's the area of the top of the rectangle? Nothing. If I choose a point in the bottom of the cross section of the rectangle, what's the area below it? 0. So my Q is 0. So my shear stress is also 0. Okay? Then I need to calculate shear stress at points E, C, and B. Okay, so this is likewise tau transverse, and the point D is also 0, so that's gone. To calculate at the point E, B, and C, I do the following. If I calculate the shear stress at point C, that is sufficient for me because the shear stress at C should be the same as the shear stress at B, should be the same as the shear stress at E, because the shear stress at all points on the neutral axis will be the same. Or if I take a line here, the shear stress at all points on this line will end up being the same value. Okay? So, I calculated at C first. So tau transverse C is VQ by IT. I'm going to just redraw the cross section once again, just to be this is my point C. Now here is what I do. What is my V? V is given as V bar. My I neutral axis is just going to be whatever the moment of inertia is. Pi by 4 or to the power 4. Please notice this is not pi by 2, this is pi by 4. Okay, because this is area moment of inertia, not the polar moment of inertia. Theta. I pass a line through the point C, parallel to the neutral axis. Point C is on the neutral axis. So starting from here, all the way to there, I pass a line which will intersect both ends of the cross section. And this thickness, or width, I'm sorry, is going to be T tau. So this is going to be 2 times R. So 2R. I need to calculate Q. A prime times y bar prime. So what's this? What is A prime? A prime is all the area either above or below the point C. Okay? So I'm going to consider all of these things. So this is going to be A prime for me. All the area either above or below the point of interest. And that's A prime here. This is the area of a semicircle. So this is half the area of the circle, right? So half pi r square. Y bar prime is the distance from the neutral axis all the way to the centroid of the semicircle, which is why we wrote down that distance there, 4r by 3 pi. Okay, so I go from the neutral axis all the way to the centroid of the shaded portion, which is some C prime, and I just call it a C prime. So the distance from there to there is my y bar prime. Okay, so y bar prime is known to me. Do the substitutions. So this is half pi r square 3 pi. Put everything together so that tau at the point C due to the transverse shear force. What is the directionality for this? The directionality is that the shear stress is going to be in the same direction as the shear force, so the first subscript is going to be the y direction. The second subscript is going to be the x-axis, because that is the axis normal to the cross section. So this is going to be yx. This is equal to v1, whatever that is. Q, which I can simplify as this pi goes off, this goes off there, I have an r cube. So 2r cubed by 3. Divided by the moment of inertia, pi by 4 r to the power 4. Multiplied by tau, t tau, which is 2 times r. Then one can crunch these things and make them shrink a little bit, but it is not our point here. This is the same as tau transverse at point E and B, okay, so not B. Okay. And you also want to mark the directionality on the cross section. That is an important thing because you're going to compare what is going on in this cross section and what is there on the torque side of the cross section. Okay. So if I draw these things, this is going to be the direction of the shear stress at point B. At point C is going to be pointing in the same direction as the shear force that was applied. So here was V1. And likewise, it is going to be the same at the point E as well. So any point you take along the neutral axis, the shear stress is going to be the same. There is no variation across the neutral axis. There is only variation above and below the neutral axis. Okay, if you're looking at shear stress, transverse shear stress. And you immediately recognize that if I look at this guy, which is pointing up in this figure, okay, so if I look at tau transverse B pointing up, I look at the shear stress at the point B due to the torque applied that's pointing down, they will be having an attenuating effect on each other. Depending on whichever is the larger, that's going to be the direction of the total shear stress there. Okay? Is everybody on the same page? Yes, question.
Can you explain the yx after the trans B, the trans E, and the trans C?
Oh, sure. So, the first subscript is the direction of the shear force, which is V1, which is pointing along the y-axis. The second subscript is the direction of the area normal to the cross-section. So whichever is the axis that is normal to the cross-section, which is the x-axis is into the cross-section, but we are not worried about the directionality from the negative positive point of view, just the suffix. Because we are anyway drawing the direction of the figure here. Okay? Alright. Any other thoughts? Yes, sir.
Wait, why is y bar prime 4 over 3 pi?
I can do the derivation, but it's going to take up half the lecture, so you have to take my word for it at this point in time. This is typically for solid lamina, okay, so 4r by 3 pi. But one can, I mean, maybe I can post the derivation on carbon, you can take a look at it. I was under the impression that statics covers these things, but perhaps not. I think I'll post the derivation just to be on the safe side.